So during a water flooding or water flood, water flood is when you have a reservoir and then you are going to push the oil out from the reservoir using water. So this water will be injected into your reservoir, which is this one, this well. So this is your injection well. We call this injection well, so we will inject water in this, and this will be your production well, where you will produce your oil. So this green one is oil, and blue one is water that you injected. So a reminder that a reservoir consists of porous rock. So this is filled with oil, the pore space. So the water injected will push the oil out of this porous rock. So will the injected water underrun the oils? So yes, because if vertical equilibrium condition exists, particularly gravitational force will dominate over the viscous and the capillary force. So vertical equilibrium is this downwards and upward verticals, and then the gravitational force is pushing the water down here. So instead of flowing like a piston, the water will flow like this due to the gravitational force and the viscosity and capillary force. So during the water flood, yes, displacement cannot be like piston-like. A vertical water flood front behind, which is immovable oil saturation, maybe. So SW equal to saturation of water equal to 1 minus saturation of residue oil W. So this one is saturation of water. Inside the reservoir is the connate water saturation. Connate. So this phenomena, which is due to the gravitational force, is called the fractional flow or the Buckley-Leverett fractional flow. So in the beginning, your water saturation is 1 minus oil residue saturation, but due to this force, the water saturation will drop to the saturation of the connate water. So for Buckley-Leverett fractional flow for one dimension displacement, so one dimension we only consider like one axis, which is the x-axis. And for example, if we have this is vertical view. So if you have your injection well here and production, the length of your reservoir is known as L, and W is the height or the width of your reservoir. And if you have an angle reservoir, you will have a theta, which is your angle. And this is the y-axis and x-axis. So your z, which is this one, the distance from the axis to your reservoir is x sin theta, and dz over dx is sine theta. So if we assume we have a diffuse flow condition at any point of x, which is this axis, two-phase oil and water may flow. So if you have your Qi, Q initial here, so initial flow rate using this is water. Water will push the oil out. The green one is oil, and then you will have Q water and QO, flow rate of water and flow rate of oil, and the out is Q total, which is both QW plus QO. From equation 14 and 15 from previous lecture, the oil and water 1D flow rates are this one. Flow rate of oil equals to this, and flow rate of water is equal to this equation. So by arranging these two equations and considering Qt equals to Qo minus Qo plus Qw, we will get this derivation after substituting the specific gravity for water and oil, and considering the capillary pressure. Your QW will now equals to this equation. And then this is the important one, the fractional flow. So fractional flow, known as FW, will be equal to flow rate of water over flow rate of water plus flow rate of oil. And if you substitute this equation, you will get your FW for a horizontal reservoir equals to this. And this is the fractional flow of water.